This page here is available on Canvas on the left-hand side navigation.
A binomial probability distribution results from a procedure that satisfies the following. First, the procedure must have a fixed number of trials. Each trial must be independent. Each trial must only have two outcomes classified into two categories, either a success or a failure. The probability must remain the same across all trials.
Next, let's discuss notation. P denotes the probability of a success, so the probability of success equals little p. Q denotes the probability of failure, so the probability of a failure equals little q. And since success and failure are complements of each other, little q equals 1 minus p, and little p equals 1 minus q. N denotes a fixed number of trials. X denotes a specific number of successes in n trials. So x is always a whole number between 0 and n inclusive. If you have, say, 12 trials, you can't have 13 successes. You can have at most 12 successes, and you can have to have at least 0 successes. P of x denotes the probability of getting exactly x successes in n trials. And we have a formula for this. The probability of x successes is n factorial divided by n minus x factorial times x factorial times p to the x and q to the n minus x.
And if you notice, n factorial over n minus x factorial times x factorial here is the same thing as n choose x, so we can rewrite our formula, as you see highlighted in yellow on the bottom right corner of the screen.
Example 1. Explain why the examples below do not represent a binomial distribution. So let's go ahead and read through all 3 of these, and then you should pause your video to write down why you think they're not a binomial distribution. A. In a U.S. cellular survey of 500 smartphone users, subjects are asked if they find abbreviations like LOL or BFF annoying, and each response was recorded as yes or other.
In a U.S. cellular survey of 500 smartphone users, subjects are asked if they find abbreviations like LOL or BFF annoying, and each response is recorded as yes, no, or other.
Part C. 10 different senators from the 113th Congress are randomly selected without replacement, and the number of terms they have served are recorded. So pause your video, take a moment, and determine whether or not these represent binomial probability distributions. So let's look at example 1, part A. We have a fixed number of trials, that is 500 respondents. Each trial is independent, that is each person's response is independent of the responses of others. 3, there are only 2 outcomes, yes or other. And 4, the probability remains the same across each trial. So part A is binomial. Pause your video again and write down your thoughts for part B if you haven't done so already. For part B, number 3 is violated. There are more than 2 outcomes. We have yes, no, and other. So for part B, this is not binomial. Now, if you haven't done so already, pause your video and write down your thoughts on part C. So let's look at part C. Since selections are made without replacement, the trials are not independent. So number 2 is violated. There are more than 2 outcomes. Senators can serve up to 6 terms. So number 3 is violated. That means number 3 is not binomial. Let's look at example 2. So let's look at example 2. Find the probability of exactly 5 tails when tossing a fair coin 7 times. So let's start by identifying our number of trials. That is n. We have 7 total trials. Let's define a success. So success is getting tails on our coin toss. And we're looking for the probability of exactly 5 successes. Now, what is the probability of a success? that's little p. The probability of getting a tails on any single coin toss is 1/2. That tells me that my q is 1 minus p, so also 1/2. And we have the probability of x equals 5 is equal to 7, choose 5. Let's start with the whole formula actually. We have n, choose x, times p to the x times q to the n minus x. Let's get our calculators. So 7 choose 5 is 21. Now we multiply this number times 1/2 to the 5th power and again we multiply this times 1/2 squared. Now I'm going to show you a bit of a faster way that'll get the same answer. So on your TI calculator, hit the second button here, and then go here to VARs, and that'll get you to the distribution menu. And scroll down using the down arrow. And you see you'll have two options. You have binomial PDF and binomial CDF. In this case, we'll use binomial PDF. Now bear with me while I write out some instructions on your screen. So again, you're going to hit the second button on your calculator and then VARs. Scroll down until you get to the letter A, binomial PDF. And here's what you're going to enter. You're going to enter binomial CDF. And then for number of trials, that's n, then your p, then your x. So in our case, we have 7 trials, a probability of 1/2, so 0.5, and we're interested in exactly 5 successes, and then paste. And see how it labeled the parentheses, just as I have this labeled here. And hit enter. And notice we got the exact same answer either way, and rounded to 4 decimal places here. So the probability of exactly 5 tails when tossing a fair coin 7 times is about 0.1640. Let's look at example 3. Given that there is a 0.85 probability that any given adult knows about Twitter, use the binomial probability formula to find the probability of getting exactly 3 adults who know what Twitter is when 5 adults are randomly selected. So our trials first. We are going to select 5 adults. And we are interested in exactly 3 successes. Our probability of a success equals the little p equals 0.85. So let's go ahead and use our calculators. And again, on your calculator, you're going to enter and once you've done that, you should get approximately the probability of getting exactly 3 adults who know what Twitter is when 5 are randomly selected is this, 0.1382. Let's look at example 4 on the top of the next page. So reincarnation belief. Based on a Harris Interactive poll, 20% of adults believe in reincarnation. Assume that 6 adults are randomly selected. Find the indicated probability. So for part A, what is the probability that exactly 5 of the selected adults believe in reincarnation? We want the probability of x equals 5. On your calculator, you want to enter we have our trials, so 6 adults, 6 total trials, and we want exactly 5 successes. So here this tells me that x equals 5. And we know that p is 0.2, since 20% of adults believe in reincarnation. And you end up with, so exactly, or about, 0.0015 adults believe in reincarnation. Let's look at part B. What is the probability that all of the selected adults believe in reincarnation? So we want the probability that exactly 6 adults believe in reincarnation. Of course, on your calculator, you have 6 trials. The probability is unchanged, and you want 6 successes. And you will end up with a very small number. So that is about, or excuse me, that can be written as a decimal. So let's look at part C. What is the probability that at least 5 of the adults believe in reincarnation? So I'm going to start with a little picture. That's 1 adult, 2 adults, 3 adults, and there are my 6 adults. So at least 5, that could be 1, 2, 3, 4, 5, or that could be 1, 2, 3, 4, 5, 6. So at least 5 So at least 5 means 5 or 6 adults. So let's see what we've already found. In part A, we found the probability of 5 adults, 1, 2, 3, 4, 5, believing in reincarnation out of 6. And in part B, we found the probability that all 6 adults believe in reincarnation. So we want the probability of x greater than or equal to 5 is equal. And what do we end up with? So the indicated probability is, or about, there is a different way we can do this. Down below, we're going to use binomial CDF. And that C means cumulative, so it counts up from 0 until the indicated probability. So let's start off with a table. Here's our random variable x and our probability of x. And we have 6 adults. At least 5 is 5 or more, so here is what we're interested in. So at least 5 out of 6. So in this section, to find the sum of this probability, so the probability of 0, 1, 2, 3, or 4 adults believing in reincarnation, you use binomial PDF. You're going to use, CDF. So binomial CDF probabilities have to add to 1. So since those have to add to 1, we can easily find this probability here. This probability is just 1 minus, the probability of x greater than equal to 5 is just going to be 1 minus the probability of x less than equal to 4, which is here. So you can write this very loosely as 1 minus binomial CDF. 6, 0.2, comma 4. And let's try this on our calculators. So 1, and of course we do minus. And let's go to our second, and then vars. And hit enter. And so our trials are 6, our probability is 0.2, and we want to count or add up the probabilities from 0 to 4. And notice we get the exact same probability. So the next example, part D, if 6 adults are randomly selected, is 5 a significantly high number who believe in reincarnation?
Let's ask ourselves a question to help answer part D.
So for part D, is the probability of exactly 5 of the 6 adults less than 0.05? If yes, then this is a significantly high number of adults with this belief. So if you recall from part A, the probability of exactly 5 adults believing in reincarnation is this. Is this number less than 0.05? It is. So yes, this is a significantly high number of adults who believe in reincarnation. Let's move on. Parameters for binomial probability distributions. So these are some of the easiest formulas to remember in statistics. Now we can use the standard deviation to help us identify significantly high or significantly low values. McDonald's has a 95% recognition rate. A special focus group consists of 1,012 randomly selected adults. For such a group, find the mean and standard deviation. So our mean is n times p, so that's 1,012 times the probability of a success. And the probability of a success is someone recognizes McDonald's, which is 95%, so 0.95. So this is 961.4. Now our standard deviation is the square root of npq, so that is 1012 inside the square root times 0.95. And again, what is q? Q equals 1 minus p, so equals 1 minus 0.95, so 0.05. And that is about, well, on your calculator you should have 6.9. So let's recall. Significantly high values are above, or 2 standard deviations above the mean. So let's compute what that is. And even though I write 6.9, use the unrounded value in your calculator and round at the very end. And what about significantly low values? So 2 standard deviations below the mean. So this one here is our usual max. Is here. And this one here is our usual min. So let's compute. Now, why did I round to whole numbers? Because people do not come in decimals. People are whole numbers. So let's write out our answer in a sentence. So we're using the range rule of thumb to find the minimum and maximum usual number of people who would recognize McDonald's. Oh, excuse me. I made a little typo here. We're rounding up. Since this is slightly more than 975 people, we round up to 976.
Let's move on to the next example.
So example 5, hybrid peas. Assume that hybridization experiments are conducted with peas having the property that for offspring, there is a 0.75 probability that a pea has green pods. Also assume that offspring peas are randomly selected in groups of 16. So A, find the mean and standard deviation for the number of peas with green pods in a group of 16. So in a group of 16, we have 16 trials. Our probability of a success, that is a pea that has green pods, is 0.75. And our Q is 0.25. So our mean is simply our number of trials times our probability of a success. So our mean is 12, and our standard deviation is equal to about 1.7. Let's look at part B. Use the range rule of thumb to find the values separating results that are significantly low or significantly high. So let's start significantly low, and this is the mean minus 2 standard deviations. And now let's try significantly high. So the usual minimum is 8.5 and the usual maximum is 15.5. Finally, is the result of 7 peas with green pods a result that is significantly low? Why or why not? So let's use the range rule of thumb as above. And let's look at significantly low values or usual minimum. So the usual number of green pods is, or minimum number of green pods is 8.5. 7 is less than 8.5. So since 7 is less than 8.5, this result is significantly low. Let's look at our last example. When purchasing, the probability that this whole shipment will be accepted. Will almost all such shipments be accepted, or will many be rejected? So let's start off by getting a handle on what we're looking at. They're going to select 50 batteries, so that means our N equals 50. The probability that they do not meet specifications is 2%, so our little p is 0.02. And finally, what are we looking for? How many batteries are we interested in? So they write at most 2. So it's accepted if at most 2 do not meet specifications. So that's 0 defective. Actually, let me move this. So we're looking for at most 2 defective batteries. So 0 can be defective, 1 can be defective, or 2 can be defective. We want the probability of x equals 0 plus the probability of x equals 1 plus the probability of x equals 2. So we can use binomial PDF 3 times as follows. And don't write this down. So don't write this down again. We can do this 3 times, or we can use the easy way. Let's use the easy way. The easy way would be binomial CDF. And if we look at our table to get a handle on what's going on, Here's our random variable, and our random variable x represents the number of defective batteries. We can have 0, 1, 2, 3, and so on, all the way to 50 defective batteries. And these are the probabilities that a battery is defective. We're interested in at most 2. So here's at most 2 defective batteries. So we want to use a binomial CDF here. And again, it's NPX, so that is our number of trials is N, 50, times the probability that a battery does not meet specifications is 0.02, comma, and then our number of trials, we want to add up 0, we want to add up the probability of 1 defective, and we want to add up the probability of 2 defective, so put a 2 here, and you get which is about 0.9216. And as a percent, that's 92.16%. Now let's answer this last question. Will almost all such shipments be accepted, or will many be rejected? 92% of these shipments will be rejected. Only about 8% will be, excuse me, I said that wrong. 92% of these shipments will be accepted. Only 8% will be rejected, so almost all such shipments will be accepted. This concludes this lecture for section 5.2.